In this video, we're going to talk about voltaic cells, which is really the basis of how batteries work. Say we have a redox reaction whose delta G value is negative. We know from previous lectures on thermodynamics that this means it's a spontaneous reaction. And redox means something is losing electrons and somewhere else something is gaining electrons. So there's going to be electrons changing places or flowing in that reaction. And so if that is spontaneous, you could imagine you set up a reaction and electrons are spontaneously moving around. And the flow of electrons like that is electricity, and we can use that to do electrical work such as light a light bulb. So the basis of how you would set something like this up and then do electrical work with it is called a voltaic cell, sometimes called a galvanic cell. And voltaic cells exploit this spontaneity criterion and redox behavior to do electrical work. So let's look at a prototypical voltaic cell. Okay, and so this is sort of like a benchtop view here if we were setting up two separate containers and connecting a wire and getting electrons to flow and do electrical work. Okay, oftentimes this is all, of course, all packaged up inside of a battery, and the wire here is, say, the flashlight you are connecting, for example. That's going to have a light bulb in it that lights up. Anyways, in a spontaneous redox reactions, electrons are transferred and energy is released. And that energy can do work if the electrons flow through some external device, like a battery. So this is a voltaic cell. And what's happening here is one of these setups is going to involve oxidation, where the zinc atoms here that are nicely and neatly packed on here are just spontaneously going into solution and leaving behind electrons. So these zincs are going from zinc solid to zinc 2 plus and generating electrons. So those solid zincs are losing electrons. That's oxidation. And meanwhile, over here, the spontaneous process is that copper 2 plus in the solution here ends up just hopping onto the copper rod and becoming solid copper. And this is a reduction, 2 plus to an oxidation state of 0. So this is a reduction reaction happening over here. And so if we connect a wire, all of these electrons over here that are being generated through the oxidation of zinc have nowhere to go. They don't want to stay here next to all the other electrons. You connect a wire and suddenly they see all the copper 2 pluses hopping onto the rod and neutralize them to make neutral copper. Right? So that's this spontaneous flow of electrons. Now, let's break this down a little bit more and build the voltaic cell to really understand everything that's happening. We're going to draw our first half cell, as it's called, on the left, and another half cell on the right. So we could just build these out of beakers and have something like zinc chloride floating around in them and copper sulfate floating around in them. And into these solutions of zinc chloride and copper sulfate, we're going to submerge a metal rod of zinc into the zinc chloride one, and into the copper one, a metal copper rod. Now, there is a spontaneous reaction that happens in the left cell that solid zinc just starts going into the solution and disappearing. That is the spontaneous direction. The opposite is not spontaneous. Zinc doesn't come out of the solution and go onto the rod. The spontaneous direction is this. And so we can write a oxidation reaction for that spontaneous process. And the electrons that are being generated here, as the zinc atom goes into the solution as zinc 2 plus, it's leaving behind its 2 electrons. Those are sort of building up on this metal rod. Now, on the right side, in this other half cell, so we have the oxidation half cell on the left, we have a reduction half cell on the right, where there is a reduction half reaction happening. of copper 2 pluses that are floating around in solution here, because this is an aqueous copper sulfate, SO4 2 minus and Cu2 plus. So there's a bunch of Cu2 pluses in the solution. They now see this copper rod and say, ha, it is favorable for me to just plate onto this rod as solid copper and neutralize a couple of the electrons in the sea of electrons here on this metal rod. And so that spontaneously occurs. The opposite does not spontaneously happen. Copper does not just dissolve off of the rod into the solution like zinc does in zinc chloride. So this is reduction, copper 2 plus neutralizing 2 electrons to have its oxidation state go from 2 plus to 0, gaining electrons. That's reduction. Whereas zinc is going from 0 to 2 plus. That is a loss of electrons, oxidation. And so the zinc rod will be disappearing and the copper rod will be growing because there's ions plating onto it and adding to its mass. Both reactions here are spontaneous. And so we're going to be generating electrons on this left rod, and we're going to be using up electrons in the sea electrons and sort of developing a positive charge on this right rod. So a bunch of negatives on the left, a bunch of positives on the right. And now say we connect a wire to this, that is going to give a path for these negative electrons to flow across the wire spontaneously from the zinc rod to the copper rod. And those could be used to power a light bulb, for example. Now, each beaker, as I've said, is called a half cell. It contains a half reaction. And each metal here is an electrode. So we have a zinc electrode and a copper electrode. And specifically, we have names for the oxidation electrode. It is called the anode. Oxidation and anode both start with vowels. That's how I remember that. Whereas reduction and cathode both start with consonants. That's how I remember that. So reduction happens at the cathode. Anode is oxidation. Electrons always flow from the anode to the cathode, which makes sense because oxidation is at the anode. That's where the electrons are being generated. And so they're going to be flowing to somewhere where they're used up, the cathode. Now, there's one last thing missing here. I'm just going to erase the light bulb so I have some space. And that is eventually enough zinc 2 plus will go into this solution that now you have all of these positive charges in here that you've generated, right? And that is not so happy to have all of these positives next to one another. Okay. And likewise, if all of these coppers are getting neutralized on the copper rod, then they're no longer in solution, right? But you still have a bunch of SO4 2 minuses. So this solution now is becoming very negative by contrast. And so what we can add to make these two half reactions to keep occurring is something called a salt bridge. And this is just a material, it's a salt, probably not sodium chloride, but something like potassium nitrate or something, but something with a cation and an anion that'll just slough off into the solution and migrate some ions into the solution to neutralize that charge. So NO3 will just start coming in here to help neutralize some of these charges, and potassium plus will start coming off into the solution to help neutralize some of these negatives, for example. And that'll allow the solutions both to stay neutral and not allow for this charge buildup, so that zincs can continually come off of the rod, generate more electrons. Those electrons can keep flowing to do more electrical work and keep lighting the light bulb. Of course, that only works up to a point, at which point then maybe your battery is dead and needs to be recharged and things need to be built back so that they can generate a Voltaic cell all over again. Okay, so that is our general setup of a Voltaic cell. Again, using two separate spontaneous half reactions that are oxidation and reduction to spontaneously flow electrons that we're going to use for something useful. Now, here's a prettier picture, again, of this voltaic cell we just discussed. Oxidation occurs at the anode, at zinc in this case, to generate electrons. Reduction occurs at the cathode, where those electrons will be used up. Electrons flow, charges aren't going to remain balanced, so a salt bridge, they say sodium nitrate here, that works too, is this U-shaped tube that contains a salt solution, and that's going to keep our charges balanced. Okay, this up here is measuring the voltage that we'll see in a few slides here, is a measure of how different in potential these two half cells are, and how much work can we then get out of this thing. For now, let's pause and try this practice problem where you're going to have to draw this voltaic cell by drawing two beakers and two half cells described here, and labeling the anode and cathode and salt bridge of each solution to make sure you understand all the working parts here of a voltaic cell. So take 2 minutes here, maybe more than that, to pause the video and try to sketch this out and label all the ports. Okay. So a chromium bar placed in a beaker that contains an aqueous solution of chromium. And then we have a silver bar in an aqueous solution of silver nitrate. The chromium bar develops a negative charge. So that's going to be like our zinc here. Oxidation is going to be happening there on the chromium, because that's where the electrons are building up. The electrons are being generated because chromium is going into solution, leaving behind its negative charge. Chromium is getting oxidized. So let's start to draw this. And I'll do this somewhat quickly. It won't be pretty. Here's chromium. It's in this chromium nitrate aqueous solution. Over here, I have silver in this silver nitrate solution. The problem told me that negative charges were developing on chromium. That means it's the chromium that is going into solution, leaving behind electrons. So this must be my anode where oxidation is happening. And specifically, it's chromium solid that is going into solution and generating electrons. Now, we know from this formula for chromium nitrate, since nitrate is -1, the chromiums here are going to be 3+. And so the half reaction here is chromium going to chromium 3+, thereby generating and leaving behind 3 electrons, right? Because our charges must balance here. On the right, we have silver. It exists in the solution as silver plus. That is jumping onto the rod to make solid silver, in the process neutralizing a single electron. Now, we can identify silver electrode as the cathode. This is reduction. It is gaining an electron. We can add our wire here. Electrons are going to flow this way from anode to cathode. And I also just need to add a salt bridge here. I'll just label it as such. And I think my drawing is more or less complete. I think it also asks us to draw or write the overall redox reaction, which means I should write and balance this redox reaction by adding these two reactions together. We sketched the experimental setup. We labeled the anode and cathode and salt bridge for each solution. We drew a wire. We showed the flow of electrons. We've written each half reaction, but now let's write the overall cell reaction. And this goes back to balancing redox reactions. Each of these is a half reaction. The other atoms are balanced. There's no oxygens or hydrogens, but we do need to add some 3s here to the silver reaction. We have to multiply this whole reaction by 3 before we add these two together so that the electrons cancel out. When we do that, we will have the balanced redox reaction shown here. This is my overall cell reaction, which is built from the two half reactions. There we go. Chromium solid plus 3 Ag plus goes to chromium 3 plus 3 Ag solids. Now, we have a name for this force that causes the electrons to flow, and it's a potential energy difference that generates this force. In much the same way that you can have water only spontaneously flowing one way in a waterfall, or this boulder sitting on this ledge up here being high potential energy, and it's going to spontaneously fall down to down here where it has low potential energy, right? Spontaneity happens from high potential to low potential energy. And the difference in the height here is some difference in delta potential energy. For our voltaic cells in electrochemistry, it's not a height difference, but it's a difference in potential energy. And that difference in potential energy in terms of electrical potential energy is the cell potential, the overall potential of the cell. And it's measured in volts. And electrons are only going to flow one way, from high potential energy to low potential energy. And that difference in the two half cells is going to be our total potential difference, known as the cell potential, measured in volts. Okay? That difference between the anode and cathode is called the electromotive force, also called the cell potential, and we're usually just going to talk about it like the cell potential and designate it as E cell, measured in volts. And it depends on the two half reactions, one of which is a cathode and one of which is an anode. And we have an exact relationship to quantify that. This cell potential overall for this voltaic cell we built is going to be found by considering the cathode reduction potential and the anode's reduction potential. The difference of these two gives us the total cell potential. And the way to think about this is, we have some process happening here, oxidation, okay? And there's some sort of potential for that to happen. And we have some process over here, reduction. There's some potential for that to happen. The difference in those two things is the total cell potential. And will be telling us something about the amount of energy involved, or more specifically, maybe the amount of work we can generate here. But it's really a energy per unit charge. That's what a volt is. A joule per coulomb. Now, when this E cell value is greater than 0, this corresponds to a spontaneous redox reaction. All right, so we're trying to design voltaic cells that when we calculate the cell potential, which I'll show you how to do in a minute, we get a E cell that is positive. That corresponds to a spontaneous reaction where electrons will be generated and flow across the wire and do electrical work. So the way we will calculate this is based on a particular voltaic cell and based on the two processes we've identified. Here's one of the half cells, here's the other. We can look up in a table, what is the potential of this half cell? What is the potential of this half cell? And take the difference to get this total E cell. All of these have been tabulated. Here's a big table of them. And so we can predict E cell by taking the difference of the numbers in this table for the two half cells involved. Now, I'll note these are all reduction potentials. And in our voltaic cells, one thing is being reduced, right? Like copper in our first example, and something else is being oxidized, zinc. Yet in this table, they're all just listed as reductions. Okay, that is okay. We're still just going to take the difference between these two numbers and do cathode minus anode. We are not going to worry about flipping any reactions. If there's stoichiometry involved in the balanced reaction, say 2 zincs to 4 electrons to 2 zincs, we don't multiply this by 2. No. When we're calculating a cell potential, we don't worry about stoichiometry. We don't worry about flipping any signs. We just come to the standard reduction potential table here and find cathode and subtract from it the anode. That generates the cell potential in volts. All of the cell potentials in this table are relative to a hydrogen electrode. We had to pick something here, right, to measure versus. And hydrogen was selected. So you can imagine having a cell where one of the half cells is hydrogen and the other half cell is zinc. And so we measure zinc relative to hydrogen and just call hydrogen 0. And the difference we get out is just zinc's reduction potential. We do it for copper. The difference we get out is just copper's reduction potential. And that's what's tabulated here. Okay, so just wanted to mention here that hydrogen is sort of the standard. So you'll see it listed in the table as a cell potential of 0. And really just everything is measured relative to this. That's how we get all these values in the table. Getting a positive cell potential, again, means the reaction is spontaneous. So if we have a voltaic cell built out of a copper at the cathode and zinc at the anode, cathode minus anode, reduction minus oxidation, gives us a positive E cell. Well, then that's a spontaneous reaction. And a good voltaic cell, electrons are going to flow and light a light bulb. Okay, so if you were shown a picture of a voltaic cell and not told the cell potential here, you should be able to identify, okay, well, electrons are flowing left to right. That must mean they're generated here. So this is the anode. This is the cathode. I go to the table and find the cathode, copper 2+1. Okay, that's here. And then I come to the table and find the anode one. Okay, that's here. And I do cathode minus anode 0.34 minus negative 0.76 to generate this 1.10. That is how we calculate E cell. Okay. Let's try slightly harder looking reaction and try to calculate E cell here. You're just going to try to find in the table 2 separate half reactions that are equivalent to this overall reaction. And you should be taking the reduction or cathode reaction and subtracting the anode reaction from that. So pause the video here and try to identify what values in the table to use and how to subtract them from one another. Pause the video here and try this, and then I will solve it. Okay. Here we can go through and identify all the oxidation numbers if we want to. Chromium here is going to be going from +6 to +3. So that looks like a reduction. So I'm probably going to be looking for this chromium species in the table, and that's going to be my cathode. And so we can come to the table here and see, well, there's only chromium listed here. It has 14 H pluses with it and 7 waters. So that seems a little weird, but we have 14 H pluses and 7 waters. So yeah, all that looks legit. And everything in red here corresponds to 1.33, and that is our cathode. Then I can look to my reaction and identify, okay, well, I minus is going from -1 to 0. So that's losing electrons, that's oxidation. So that's the anode. And so I want to come to the table and find I minuses and I2s, I minuses and I2s. That corresponds to this value. As I said before, stoichiometry doesn't matter. So just because there's a 6 and a 3, whereas these say 2, I don't multiply through this number by 3. I don't do anything due to the stoichiometry here. I'm just using the 0.54 value for my anode reduction potential. And I'm just doing the cathode minus the anode, 1.33 minus 0.54. That should give us 0.79. That is how we calculate the cell potential for this problem. This is greater than 0, so this would be a good voltaic cell with a spontaneous redox reaction overall. We would expect delta G to be negative for this spontaneous reaction, just to tie it back to thermodynamics here. Now, one last concept to cover here, and that is just thinking about the order top to bottom of this standard reduction potential table. Okay, up at the top, where there's the largest reduction potential values here, okay, those are the easiest things to reduce. Those are the things that want to be reduced the most, the things that want to gain electrons. So no surprise, it's halogens. They love to gain electrons here. And down here at the bottom, these are the things that are hardest to reduce or easiest to oxidize. Okay, things like alkali metals, sodium and lithium, always want to lose their electrons, so they're going to be at the bottom of the table, the lowest or most negative reduction potentials, because they tend to want to be oxidized instead. All right, so the more positive the reduction potential, the easier these things are to reduce. The more negative the reduction potential, the easier they are to oxidize. And to tie this back to a previous lecture where we talked about oxidizing and reducing agents, the things at the top are the strongest oxidizing agents. The things that are easiest themselves to reduce, but are going to strongly oxidize something else, right? So these halogens that want to gain electrons are very good at causing a loss of electrons from things like alkali metals. So these things at the top that are easy to reduce are going to be very strong oxidizing agents. They're going to be causing the oxidation of something else. And vice versa, the things at the bottom here are strong reducing agents, themselves being easy to oxidize. So you will have to look at the table and arrange things according to their strength as reducing agents or oxidizing agents. So rank these from strongest oxidizing agent to weakest oxidizing agent. Pause the video for a minute here and try it. Okay. If it's the strongest oxidizing agent, that means it wants to be reduced the most. And it is going to be towards the top of the table the most. That's where the strongest oxidizing agents are. Whereas the weakest oxidizing agent is going to be the thing that itself doesn't want to be reduced. Okay. And so we just have to look for these species in our table here and find out where they are top to bottom. Cr2O7 is this row. NO3 minus is here. And Ag plus is here. So the thing that is highest up, Cr2O7, that is the strongest oxidizing agent. It is going to be the thing that is best at causing the loss of electrons for something else because itself is really wanting to be reduced and gain those electrons. So Cr2O7 2 minus is the strongest oxidizing agent. Then going down our reduction table, we get to a weaker oxidizing agent, NO3 minus. And finally, the weakest or lowest down amongst these three is silver plus. So that is the order we were looking for here. Higher in the table are stronger oxidizing agents. If the question was about reducing agents, well, then it would be flipped. Things towards the bottom are the better reducing agents, as shown here. So that'll do it for this lecture. Next time, we're going to connect this back to delta G and spontaneity in thermodynamics with some formulas and develop something called the Nernst equation, which will let us calculate cell potentials and things for setups where maybe not everything is standard conditions and 1 molar and happy, because life is messy. There's going to be sort of alterations. And so the Nernst equation will allow us to do this for non-standard conditions. But that'll do it for this lecture. See you next time.